on a proposal now to do more investigative work here with radiocarbon, but you can see that the shapes are different. The only place that we see that bimodal shape is here in the Narayani, but it seems to be highly related to the actual geology of the individual drainage basins within the Himalaya, as to how much of this high temperature, high age, low radiocarbon there is in the systems. And then we have one sample, this blue curve, that's down here near the confluence of the Brahmaputra and the Ganges River. And this shows some evidence that some of that bimodality is preserved there. And we're going to investigate that further with more dating. But the question of what happens to this green curve as we move downstream is very important, right? Do we simply just dilute the petrogenic carbon and bury it out here in the Bay of Bengal? The Bay of Bengal is so overwhelmed as a marine system by all of this carbon coming in from these two major river systems in the very high mountain range that almost 100% of that is buried. There's not much reworking, even with resuspension and everything. There's not, once carbon comes down to this point, it normally is on a beeline for the rock carbon cycle. It's not going to come back out into the atmosphere and be involved much in the atmospheric and biological carbon cycle. So if there's a change, for instance, if we didn't see any change in that bimodality, basically that would then imply that we're just moving carbon from an old reservoir back to an old reservoir, and it wouldn't affect atmospheric compositions too much. But this graph behind here hints that we do see some changes, and we want to get our hands on that, and using the isotopic approach would be the best way to do so. So now we're getting into large rivers. So this is a map of the Mississippi River with the Atchafalaya outflow here. These are some areas that we sampled when I first arrived at Tulane University and witnessed a high water event. And I thought it would be really interesting to compare a high water event to a regular flow system and see if there was a big difference in age spectra. These are just hydrographs and sediments with the same sampling there. And for those of you, I always call this Mars for the Mississippi River system, but sometimes if people look at the text and don't really look at the maps, they might think that we're doing this for samples on Mars, and we're not that well known yet, I guess. But in any case, these two columns are samples from different flow regimes, different discharges, and this is during high discharge in 2008, and this is during near mean discharge in 2009. And it's at different depths, so that's near the surface, that's halfway down, and that's 0.9 of the river depth at the point where we sampled. It's a lot of data to digest, but the main thing to look at is that the age spectra during the high discharge are normally higher than the low discharge. Okay? And what that showed us is that this transport of older continental carbon to depositional centers like the continental shelf and the deltaic plain are biased by older carbon, because these events, these high water events, are disproportionately responsible for those deposits. The amount of sediment in a river increases as a power function with the discharge of a river, the water discharge of a river. So this is a fairly important finding. However, you'll notice that the age axis here is not nearly as big as it was in the small mountainous rivers where we had ages up to 30,000 years. So the question is, that for next week, is a deltaic deposit dominated by the older age spectrum OC? And what we can do here is we do this Gaussian modeling again. In the case of the Mississippi, it really only gets solved with three different components. And we find that during higher discharge, there's a 130 to 530% increase in that in the fraction of C3 here. It's a small overall contribution of older POC, but it is a large relative increase. But probably the most important part here is that there's a small overall age range, or the age spectra are much narrower than we would have hypothesized when we went into this, because the Mississippi River, when you think about it, it's draining coal fields in West Virginia. It's draining old carbonates in Montana. All of that's coming down the river. Where is the old carbon here? We really don't see it. So it's very interesting. Now, this is sort of a conglomeration of both the SMR work and the large river work. All of those plots that I just showed on the last one from the Mississippi are shown here, as well as the Ganges Brahmaputra. And they actually, what I did here is I plotted them with colors based on the maximum minus the minimum radiocarbon age in the age spectrum. So you see that the Ganges Brahmaputra here, the Narayani River, has consistent wide age distribution spectra because they're in the red, and they have these bimodal spectra. Whereas the Mississippi River, over several different discharges, where we show that there's differences between those discharges, but when you compare it to a different river basin, the differences are sort of washed out. You can't see any differences in these colors. The age spectrum is pretty much always the same: high flow, low flow, whatever flow. So more recently, we've gotten involved in analyzing some Eel River sediments that were sent to me from Neil Blair. And this is a picture of the sediment plume from the Eel River. The Eel River is a small mountainous river, but it turns out that small mountainous rivers are very important for the carbon cycle because, one, there's a lot of them. There's only a few major rivers in the world by definition, right? But a lot of the rivers are smaller, and a lot of those drain mountainous systems. And because they're draining in a steep basin on these active margins, they're cutting into the rock and transporting a lot of sediment per flood event. And they're very episodic, but overall they have a lot of bang for their buck in delivering terrestrial carbon to the oceans. This is a map of the elevations here. It's nothing like the Himalayas, but this is a pretty steep drop compared to the Mississippi, right? And you can see that in this picture from the river itself. The Eel River, why we picked that one, it's a well-studied model. It's sort of the model for small mountainous rivers. And this is thrown on the same plot. Now, it looks like a mess, and I do this on purpose. I mean, you're not supposed to be able to tell anything about any one curve, but there's groups that show up here. I put the Eel River curves. There's 3 samples here in heavier lines. And again, you see the Mississippi in these thin blue lines. You see the Ganges Brahmaputra in red, very different age spectra. The Eel River looks just like the Mississippi. So at face value, it looks like our sort of support for this conceptual model is breaking down. Here we have this model of a small mountainous river, and by our method, it's plotting out just like the Mississippi. Well, it's not that simple, because here we're looking at the actual, just sort of a parameter of the age spectrum, the maximum minus the minimum. But if we look at, for instance, the minimum ages, the Eel River actually is delivering overall much older material on a whole. Then even here, the Ganges Brahmaputra system disappears because its spectrum is so wide that it has very young, and it also has very old ages. So here's the oldest ages, and now again in the oldest ages you see the difference between the Mars and the Ganges Brahmaputra, and again the Eel River is different here, and it kind of represents a continuum. In fact, when I first drafted this figure, my wife made fun of me. And this is what happens to dating, later in life, especially if you date scientists. Is that my wife makes fun of me because of my use of a color bar here. She said, "Why would you use a color bar when you only have 2 colors? Why don't you just call one, old and the other one new?" And I said, "Well, this is just. I know that one day we're going to find samples that fall in between here." And she said, "Okay, whatever." And and then we ordered appetizers. So here we have it. We found it. I haven't even shown her this yet, but it reminds me that I better bring this home and show her. We'll have a great Valentine's night. We found this sort of this middle member. So the Eel River, we've used it as a model for small mountainous rivers, but maybe it's sort of in a continuum. It's not as good a small mountainous river as the Narayani was. So now, switching back to the large rivers, one of the most interesting and newest findings that we have is from the 2011 flood, the biggest flood on the Mississippi River system. We did a lot of sampling on the Atchafalaya outflow here. These sample sites are my colleague Brian Roberts at LumCon, who's visited these sites for monthly, over 80 months now. Pretty impressive sample set. And we can't do that much work, so we asked them for seasonal samples. And then when this flood came up, we sampled a little bit higher frequency, and we got the whole hydrograph. And this is the offshore sample, the furthest offshore one that we take from him. And we have another age spectrum here, very young. This is during, this is right after the peak flow of the 2011 high water event. You can see that the ages get older with temperature, but they don't get very old at all. And there's a lot of actual bomb radiocarbon in this sample. This was sampled at 0.5 meters depth. And when you get out to this point, the water is only about 3 meters deep. But at about 1 meter, there's a very sharp halocline. So you have fresh water on top that's being sourced from this river. And as you drop a CTD down or just a salinometer, you can find salinities of about 20, 22, 25 at the bottom. And it's a very abrupt change from about 0.5 to 20 to 22. Okay? And so this sample's above that halocline. And this sample's at the same exact spot 5 minutes later below the halocline. So we see a big increase, relatively speaking, in terms of the age of the sediments. And to me, what this is saying, we have more data to support this, including the stable isotope data, which show very light terrigenous values, about an average of 9.7 above the halocline. And we're missing 1 point here that the sample got lost, but you're down to about negative 26, 27. Still pretty terrigenous, but heavier as you go down. And what it seems to be happening is in this small space, as a particle comes through, the halocline doesn't stop the particles. The particles can go through the halocline. What we think we're seeing is very rapid diagenesis of the organic material. And these types of environments, as we all know, are very productive from the microbial level all the way up to the macrofaunal level. And what we think we're seeing is that the microbes are getting at the carbon and taking advantage of the youngest carbon first, which is easy to eat. The same reason it burns at lower temperatures in our dirt burner is the same reason that one would want to try to obtain some nutritional value from it, because it's relatively easy. And what gets left over is what we end up seeing in the particulate organic carbon, and it's older. So this is, we're talking about changes in thousands of years now over the whole river system and through different, thousands of kilometers and times of years in the Mississippi River. In our former data set, we were only seeing changes of a few thousand years. And here we are measuring over a meter in the water column at the same location and seeing this. And that to me is very interesting. It also shows how important the marine system is to changing this carbon signature. And that might not be as well represented in this model as it could be. But just to recap where we fit in terms of testing this model, it does show that the age spectra differ depending on river type, and it supports the model pretty well. Now, this model, there's one big area that it doesn't really take into account, and that's rivers that are draining frozen sediments and high latitude rivers that are going into the Arctic Ocean, for instance. And those are becoming more and more important as we think about our carbon cycle. If those are warming, what's going to happen as that permafrost starts to erode? And that's something we've just started to tackle. And also land use change, which is becoming as big a factor in studying environmental change as climate. We have two small data sets that I'll just sort of scratch the surface of here. The first one is for high latitudes. It's the Colville River. It's a river that entirely drains permafrost. So something, when people think of Arctic rivers, they usually think about the Mackenzie in North America. Well, that's starting off at actually a pretty low latitude, relatively speaking. The Colville River, on the other hand, is entirely permafrost. So if we see any changes in sediment from the Colville River, we would expect that to be because of changes in the permafrost and not simply just changes in erosional patterns throughout a large basin like the Mackenzie. And this is these are samples given to me by Tom Bianchi, who's now at the University of Florida, and his student Katie Schreiner, who's now at Northwestern. And they have a bunch of sites here. We picked two. One is in the deltaic deposit, the submarine delta, and the other one is sort of along the longshore drift or the lagoonal deposits here. Okay, and what we did here is not only did we analyze age spectra, if that's not confusing enough, but we took the sediment and we separated it by density. And then for each density fraction did an age spectrum. So it's sort of like 4 dimensions of sampling here. This is, all of these individual curves are from the different density fractions. If we add them up together, in some cases we get a good shape. In some cases we get a good match of the bulk age. This is sort of a mixed result. We would have had this shape match on both of them. The gray is adding up all of these curves, and the black is just measuring the bulk sediment without separating by density. This one didn't go so well in terms of that, but the ages matched up very well. This one went well in terms of matching up the pyrolysis chemistry, but the ages were pretty far off. So we're optimists. We take this as good news, though we kind of ignore the bad news there. It's only 2 samples, but we think that there were some issues with it that we could do. But what this gives us is a lot more data, and it allows us to compare it to something else, which is the Lignan ratios. This lambda term is basically how much of that organic material is made up of lignin. Now, for those of you who don't know, lignin is a class of compounds that is only formed terrigenously. So when you find it in the ocean, you're pretty much guaranteed that you're talking about a terrigenous input to ocean carbon, to marine sediment carbon. So it's been very useful through time. And what we see here is that when we get into more lignin, we have younger ages. So we're washing more lignin down the river. We have younger ages. Interestingly, we have a higher Tmax, and this goes to some of my graduate student Elizabeth Williams' work, where she's burning individual compounds and finding out where they lie. Lignins are actually hot burners, even though they're young. But this was an interesting finding. Basically, to make a long story short, what we're seeing here is that we're seeing the breakdown of Yodoma deposits in the river sediments, which is probably related to warming. But in the lagoonal sediments, we don't see much evidence of this Yodoma, but what we do see is coastal erosion of permafrost. And basically the permafrost and Yodoma have different lambda values here, and they're separating out pretty well. You see all the L's here and all the D's here. This is deltaic and this is lagoonal. So some pretty interesting results here. We've just submitted these to GRL last week, actually. And then sort of the final problem that we're taking on with this carbon cycling questions using the dirt burner is land use change. And this is a map of different river basins in the world and how much they are affected by dams. And there are hundreds of thousands of dams on river systems now for all different purposes, from the grand dams for hydrologic purposes to just small flood control and irrigation structures. But basically this transit in our conceptual model of sediment going from mountaintop to the ocean, it's important to realize that that's becoming more and more interrupted. And when you build a dam, you end up stopping a lot of that sediment and sort of fractionating grain sizes that end up going down the river afterwards. So we want to know what happens to sediment and its carbon if it's trapped behind these river systems. And in gearing up to do some coring of these catchment basins, we started to look at a core here at Lake Whittington, which is an oxbow lake, and it has the reason we chose this for a preliminary study is that it was an artificial oxbow, and that the Army Corps of Engineers cut the channel through here to make it a straighter flow. And this now just receives episodic sediment during high water events on the Mississippi River. And other people have worked on cores that have been taken from this. They're well dated. They have good records of pollutants. It's very high, still very high sediment accumulation, and there's high carbon, so we can throw the dirt burner at this. And there's a lot already known about this. So this is an example where we might not be analyzing T0 sediment anymore, but we're analyzing sediment for which we know the age. So that means we can use the radiocarbon not for chronology, but for carbon cycle questions. And so far what we found, I've just started getting some results in. These are the curves going down core. This is core depth now. All of the curves look just about exactly the same. There's not much change in chemistry as we go down cores, and I've kind of given you an idea of the time scale of these samples. But what's interesting is that I have 5 samples and I have 5 incomplete radiocarbon data sets, but what we see evidence of is that there's a age reversal between about 150 and about 200. So somewhere in the late 40s, early 1950s, there was younger radiocarbon down here than up here. And that's very interesting because there's been so much land use change, and we're getting into the Dust Bowl and different erosive events, and what we want to see is the building of these dams plus the spread of agriculture. Did that have an effect on the way carbon is cycled in the Mississippi Basin? And basically the records are going to be locked up here in the sediments behind these dams. So basically, in sum, I think one of the biggest things that we offer with the ramp pyrolysis system is that even though we've really improved analytic precision of radiocarbon dating, a lot of people are very satisfied when they send off a sample and they get a radiocarbon date back that's plus or minus 10 years or plus or minus 15 years. But especially students, one thing that you have to ask is, what does that mean? What is analytical uncertainty, and how does that relate to what you're actually studying? And I like to coin this phrase, geologic or environmental uncertainty is more important. So at the very least, if you didn't believe anything that I was saying, when you look at the age spectra that are coming out of our method, that gives you an idea right there of what the geologic uncertainty is in a radiocarbon age, and it's orders of magnitude greater than the analytical uncertainty. So it's an important component of our work, and I think it gets by a lot of people that review it and everything. But some of the later studies that you've seen that we're doing, we're trying to couple this with more refined techniques, compound-specific radiocarbon dating, that biomarker work, where you really pinpoint processes. And what we look at, our role is relating those processes that you might draw really big conclusions from 0.1% of the carbon and relating that to what the whole age spectrum is of all of the carbon in this system. So with that, I'd like to thank you and invite any questions.
One of the later figures was the areas affected by dams, not affected, somewhat affected.
Mm-hmm.
What are the white areas, like Florida?
Either no data or no rivers. Like, for instance, the Sahara is white.
Well, Florida is white, too.
Yeah, so I think it's just no data. They just didn't take data. Yeah, and this is actually back in 2004. There's been which is not that long ago, but the amount of dams since then, it's something like, in the Mississippi River system, it's like 80 dams per year. Because we're not talking about damming the Mississippi River system. We're also talking about a dam up on a meadow, a highland meadow that's draining into the Missouri River, that's draining into the Mississippi River. The USGS has really put a lot of work into trying to quantify where active dams are, where dams are breaking. They're trying to have that initiative. I don't know much about the USGS's activity in river monitoring in Florida, but
southeastern U.S. as well, East Coast.
yeah.
There's nice rivers there.
Yeah, and there's a lot of dams there too. So this is an underestimate.
Talking about